In 1883, the sky changed. Not in one country. Not over a single ocean. The change was visible across continents. From Europe to North America, from India to the southern seas, evenings began to unfold differently. Twilight lingered. The horizon glowed in deep crimson bands long after the sun had disappeared. The atmosphere seemed altered, though no one yet understood why. In London, observers described sunsets that burned with unusual intensity. Layers of red and violet stretched across the western sky, suspended as if trapped at high altitude. The colors were not fleeting. They persisted, expanding slowly before dissolving into darkness. Painters recorded the scenes with precision, uncertain whether they were capturing beauty or documenting disturbance. Reports soon followed from Paris, Rome, and Stockholm. The phenomenon was consistent in structure yet unfamiliar in tone. The glow extended horizontally, diffused through a faint haze that softened daylight and intensified dusk. Newspapers treated it as a curiosity, but scientists began to notice patterns. The timing was too regular. The scale was too broad. Across the Atlantic, ships logged luminous horizons weeks after the first European sightings. In India, similar displays were recorded at comparable latitudes. The effect did not respect borders or seasons. It moved through hemispheres, repeating itself with striking uniformity. Whatever had changed the sky had done so at planetary scale. Meteorologists lacked the tools to measure the upper atmosphere in detail, yet optical observations pointed toward fine particles suspended far above ordinary weather systems. Light was being scattered differently. Solar radiation bent and diffused in unfamiliar ways. The disturbance was not meteorological in the conventional sense. It originated from a different layer of the planet system. Artists inadvertently preserved some of the clearest evidence. Paintings from late 1883 and 1884 show exaggerated red horizons once dismissed as stylistic flourish. Yet many were observational records. They captured a genuine atmospheric transformation. The world did not simply look different. It was physically interacting with sunlight in a new configuration. The phenomenon persisted through winter. Reports from transoceanic routes described a diffuse veil high above cloud formations, visible at dawn and dusk alike. The effect did not dissipate with passing storms. It remained steady and global, suggesting that a vast quantity of material had been injected into the upper atmosphere and was circulating beyond ordinary weather cycles. Scientists began asking a decisive question: what event could propel matter high enough and in sufficient volume to alter the optical character of the entire planet? Industrial smoke was insufficient. Desert dust could not explain the uniformity. The source had to be sudden, violent, and capable of reaching extreme altitude. The answer lay thousands of kilometers away, in a narrow maritime corridor between Java and Sumatra. In late August of that year, a volcanic island in the Dutch East Indies had undergone a sequence of detonations so powerful that they restructured the surrounding sea. But the most enduring consequence was not local destruction. It was atmospheric transformation. Before Europe noticed its crimson evenings, before scientists recalibrated their instruments, an island called Krakatoa had torn itself apart. The unusual skies of 1883 were not a coincidence of weather. They were the lingering signature of an eruption that reached beyond geography and entered the climate system of the planet. Months before the skies turned red over Europe, the Sunda Strait lay between two vast landmasses of the Indonesian archipelago. Java to the east, Sumatra to the west. The corridor was narrow, strategic, and restless. Beneath its waters, the Earth's crust was not stable ground but a boundary between converging tectonic plates. The Indo-Australian plate moved steadily northward, descending beneath the Eurasian plate in a process that unfolded invisibly over geological time. This subduction zone formed part of the Pacific Ring of Fire, a vast arc of seismic instability stretching across oceans. The strait was not simply a passage for ships. It was a structural seam in the planet's crust. Along this seam rose a cluster of volcanic islands. Among them stood Krakatoa, positioned roughly at the center of the strait. It was neither the largest nor the tallest volcano in the region, yet its location made it significant. It stood directly above the zone where oceanic crust was being forced downward into the mantle. For centuries, the island had erupted intermittently. Ash deposits layered the surrounding seabed, and earlier explosions had reshaped portions of its structure. Yet by the late 19th century, Krakatoa appeared quiet. Maritime routes passed nearby without hesitation. Colonial trade moved steadily between the ports of Batavia and the broader Indian Ocean. Beneath the apparent calm, pressure accumulated. As the descending plate sank into hotter depths, water and volatile compounds were released into the overlying mantle. This process generated magma, which gradually rose toward the surface. The mechanism was slow, but the energy involved was immense. The strait concealed a system under increasing stress. The configuration of the region amplified its volatility. The seabed around Krakatoa was irregular, with submerged ridges and basins shaped by earlier volcanic episodes. Any significant eruption would not occur in isolation. It would interact with water, with confined geography, and with densely navigated sea lanes. In early 1883, subtle signs began to surface. Minor tremors were felt along the coasts of Java and Sumatra. Fishing communities reported faint rumblings beneath the sea. The disturbances were not yet alarming, but they were measurable. Instruments in colonial administrative centers recorded unusual seismic patterns. By May of that year, visible activity intensified. Columns of ash rose intermittently above the island, carried by prevailing winds. Explosions were heard across the strait, though their scale remained uncertain. Krakatoa had re-entered the historical record, but few anticipated the magnitude of what was developing. The geography of the strait ensured that any major eruption would not remain confined to the island itself. Water, trade routes, and coastal settlements lay within immediate reach. What appeared to be a local volcanic reawakening was unfolding in one of the most strategically situated maritime corridors of the 19th century. The skies of Europe would not change for several months. But the mechanism that would alter them had already begun to move. Beneath a narrow strait between continents, pressure was building toward a release that would exceed all regional expectations. By the middle of May 1883, Krakatoa was no longer quiet. Ash columns rose several kilometers into the sky, visible from coastal settlements across the Sunda Strait. The eruptions were intermittent but increasingly forceful. Each explosion signaled that magma was moving through newly opened fractures within the island structure. Ships navigating between Java and Sumatra reported falling ash and distant detonations. The sound carried farther than expected, echoing across open water. Yet trade did not halt. The region had known volcanic unrest before. Few imagined that these disturbances marked the beginning of one of the most powerful eruptive sequences in recorded history. Throughout June and July, activity intensified. Multiple vents opened across the island, releasing ash and steam in sustained bursts. The eruption column widened and darkened. Lightning flickered within the plume, generated by charged particles colliding in turbulent updrafts. The atmosphere above the strait began to behave unpredictably. Seismic readings in Batavia showed escalating tremor patterns. The data suggested magma was not confined to a single chamber. Instead, the volcanic system appeared interconnected, with pressure redistributing beneath the island. The internal architecture of Krakatoa was destabilizing, though its full configuration remained unknown. Ashfall affected nearby coastlines, coating vegetation and rooftops in fine grey dust. Daylight dimmed intermittently when winds shifted. The event was no longer an isolated geological curiosity. It had begun to intrude into daily life, altering air quality, visibility, and maritime navigation across the region. Underwater, the situation was even more volatile. Magma interacting with seawater created explosive phreato-magmatic reactions. Each interaction fragmented rock into finer particles, increasing the explosivity of subsequent eruptions. The confined geography of the strait amplified acoustic shock and wave displacement. By late August, Krakatoa was effectively operating as a complex, multi-vent system under extreme internal stress. The eruption columns now rose high enough to enter the upper troposphere. Ash clouds spread laterally, carried by high-altitude winds that would later disperse material across continents. Despite the escalating violence, no comprehensive evacuation occurred. Coastal settlements remained occupied. Maritime routes continued to function. The 19th century possessed neither satellite observation nor rapid communication networks capable of conveying the true scale of what was developing. On the evening of the 26th of August, 1883, activity intensified dramatically. Continuous eruptions merged into sustained detonations. The island's structural integrity was failing. The volcanic system had crossed a threshold from episodic eruption to catastrophic destabilization. The world would soon hear what was happening in the Sunda Strait. But before the sound traveled across oceans, the island itself was beginning to tear apart under pressures accumulated over centuries. In the early hours of the 27th of August, 1883, Krakatoa entered its final and most violent phase. The eruption, already intense the previous evening, escalated into a sustained sequence of catastrophic detonations. At approximately 5:30 a.m., one of the largest explosions shattered the morning air, propelling vast quantities of ash and fragmented rock high into the atmosphere. The force of the blast was not merely audible, it was concussive. Windows rattled in Batavia, more than 100 kilometers away. Ships in the strait recorded violent pressure waves striking their hulls. The sound traveled with extraordinary clarity across open water, amplified by the confined geography of the region. 3 additional major explosions followed over the next several hours. Each surpassed the previous in energy release. The eruption column expanded dramatically, punching through the upper layers of the atmosphere. Ash and volcanic gases were injected to altitudes rarely observed in historical eruptions. Shortly after 10 a.m., the most powerful detonation occurred. The blast generated a pressure wave so intense that it would later be recorded thousands of kilometers away. Observers close to the strait experienced not a single sound, but a physical shock, an abrupt compression of air that swept across land and sea. The energy released during these explosions destabilized the internal structure of the island. Magma chambers emptied rapidly, removing support beneath large sections of volcanic rock. The surface could no longer sustain its own weight. Structural collapse became inevitable. As portions of Krakatoa's edifice gave way, the island began to implode into its own evacuated magma chambers. This was not gradual erosion. It was caldera collapse, an abrupt reconfiguration of geological mass. Entire sections of the island subsided, altering the topography within minutes. The collapsing material displaced enormous volumes of seawater. The Sunda Strait responded immediately. Waves radiated outward from the island, shaped by underwater ridges and coastal contours. The event was no longer confined to the atmosphere. It had become a maritime crisis. Meanwhile, the pressure wave from the final explosion propagated outward at the speed of sound. It crossed the Indian Ocean, reached Australia, traveled toward Africa, and continued around the globe. Barometers registered sharp oscillations as the atmospheric disturbance passed overhead. The eruption did not simply destroy an island. It injected material into the stratosphere and sent a measurable pulse through the atmosphere of the entire planet. The detonation of the 27th of August was not a regional disaster. It was a planetary event unfolding in real time. By midday, much of Krakatoa had disappeared beneath the sea. What remained was a transformed landscape and an atmosphere already carrying the consequences far beyond the horizon of the Sunda Strait. The collapse of Krakatoa did not end with the final explosion. As the island subsided into the sea, immense volumes of water were displaced within the narrow basin of the Sunda Strait. The sudden alteration of the seabed forced the surrounding ocean outward in rapidly forming waves, generated not by wind, but by geological collapse. Along the western coast of Java, the sea first appeared to withdraw. Harbors briefly exposed sections of seabed normally concealed beneath shallow water. Fishing vessels tilted awkwardly in receding tide. The retreat was unnatural in speed and scale, a visible signal that mass had shifted offshore. Minutes later, the returning surge arrived. The advancing wall of water moved with accelerating force, driven by the confined geometry of the strait. Low-lying settlements had little warning. Structures nearest the shoreline were overwhelmed first, followed by successive inland surges as reflected waves rebounded between opposing coasts. Across the strait in Sumatra, similar conditions unfolded. The pattern was not uniform. Local topography determined the height and reach of each wave. Some areas experienced a single devastating impact. Others endured multiple oscillations as the basin amplified residual energy from the collapse. Maritime traffic was caught within unstable currents. Ships encountered rapidly shifting water levels and floating debris carried by the surge. Navigation became impossible not because of storm winds, but because the sea itself was reacting to a change in underlying geography. The tsunamis did not consist of a single crest. They propagated in sequences, interacting with submerged ridges and coastal contours. Reflected waves extended the disturbance over hours. The strait functioned as an enclosed system, intensifying and redistributing the energy released by the implosion. Communication between affected regions deteriorated rapidly. Telegraph lines failed in several locations, and ash continued to fall intermittently. Reports from different coastlines emerged fragmented and delayed. No central authority immediately grasped the full extent of the maritime impact. Entire coastal communities were displaced. Infrastructure vital to colonial trade networks suffered severe disruption. Yet even as regional devastation unfolded, the atmosphere above the strait was carrying a different consequence upward, fine particles rising beyond the reach of weather systems. What occurred along the shores of Java and Sumatra was immediate and visible. But the most enduring transformation was already unfolding at high altitude. The same eruption that reshaped coastlines had propelled material into layers of the atmosphere capable of altering the behavior of sunlight itself. While the waters of the strait gradually receded, the upper air continued to circulate ash and sulfur compounds across hemispheres. The regional disaster was measurable in destroyed harbors and altered coastlines. The planetary effect would reveal itself more slowly, in light, temperature, and climate. The explosions of the 27th of August did more than fracture an island and displace the sea. They generated atmospheric shockwaves of extraordinary intensity. The final detonation, shortly after 10 a.m., produced a pressure pulse so powerful that it traveled outward across the surface of the Earth, compressing the air as it moved. Barometric instruments in Batavia recorded a sudden spike. Hours later, similar oscillations appeared in India. The disturbance continued westward, reaching the Arabian Peninsula, Africa, and Europe. Within days, meteorological stations across multiple continents detected the passage of the same pressure wave. The shock did not dissipate after a single circuit. It circled the globe at least 3.5 times, with barographs worldwide registering up to 7 passages over 5 days, 4 outward and 3 returning, gradually weakening but remaining measurable for several circuits. For the first time in recorded history, a volcanic explosion had been tracked in real time at global scale. Sailors thousands of kilometers from the Sunda Strait reported hearing distant detonations long after the eruption had occurred. In parts of the Indian Ocean, the sound was described not as thunder, but as sustained artillery. The atmosphere had become a transmission medium, carrying acoustic energy across oceans. The magnitude of the sound challenged comprehension. Later analysis would classify it among the loudest events ever documented by human observers. Yet its importance was not merely acoustic. The same force that generated the shockwave had propelled ashen gases to extreme altitudes. As the eruption column rose, it penetrated beyond the lower atmospheric layers governed by ordinary weather. Fine particles and sulfur compounds were injected into the stratosphere, where circulation patterns differ from those near the surface. Material reaching that altitude can remain suspended for extended periods. The shockwave and the ash plume were interconnected expressions of the same energy release. One traveled horizontally through air as pressure. The other rose vertically, entering a region where sunlight interacts differently with suspended matter. Both signaled that the eruption had exceeded regional boundaries. Scientific communities began comparing barometric readings from distant stations. The alignment of data confirmed that a single event had produced measurable atmospheric disturbance across hemispheres. The Earth's atmosphere had responded as an integrated system. In the 19th century, this level of planetary connectivity was still being understood. The eruption of Krakatoa provided a demonstration more persuasive than theory. An event in a narrow tropical strait had registered in instruments thousands of kilometers away within hours. The sound that circled the Earth was not only a record of explosive force. It was evidence that the atmosphere links continents through shared physics. What had begun as a geological rupture was now manifesting as a global atmospheric experiment unfolding above every nation. When Krakatoa erupted, it did not simply scatter ash across nearby seas. The most powerful explosions forced enormous quantities of fine particles and sulfur-rich gases upward into the stratosphere, a region of the atmosphere that lies above ordinary weather systems. Material reaching this altitude behaves differently from volcanic debris confined to lower layers. In the troposphere, ash is rapidly removed by rain and turbulence. In the stratosphere, however, precipitation is absent. Circulation occurs on a broader and slower scale. Once injected into this region, particles can remain suspended for months to years, gradually spreading across latitudes through high-altitude wind patterns. Among the most significant emissions were sulfur dioxide gases. At high altitude, these gases underwent chemical reactions, forming sulfate aerosols, microscopic droplets capable of reflecting and scattering sunlight. This transformation altered the radiative balance of the atmosphere, modifying how solar energy entered and exited the climate system. The concentration of aerosols increased progressively as stratospheric winds transported them around the globe. Within weeks, measurements of atmospheric transparency began to shift. Sunlight appeared filtered. Daytime brightness softened slightly, while dawn and dusk intensified in color due to enhanced scattering of shorter wavelengths. Unlike surface dust storms, this was not a transient event tied to seasonal patterns. The aerosol veil persisted. Its distribution became increasingly uniform across hemispheres, demonstrating that the stratosphere functions as a global conveyor rather than a collection of isolated air masses. Temperature records from the years following the eruption reveal a measurable cooling. Global average surface temperatures declined by approximately 0.5 to 0.6 degrees Celsius in the year immediately after, with effects lingering for up to 5 years in some records. The cooling was not catastrophic, but it was significant enough to confirm that volcanic activity can influence planetary climate. Agricultural reports from certain regions described altered growing conditions. In some areas, harvest cycles shifted slightly due to cooler summers. While multiple factors influence climate variability, the temporal alignment between the eruption and subsequent temperature anomalies strengthened the connection. For scientists of the late 19th century, Krakatoa provided an unexpected case study. It offered empirical evidence that a single eruption could affect atmospheric composition at planetary scale. The concept of climate as a globally interconnected system began to gain stronger observational support. The red skies observed months earlier were therefore not merely aesthetic curiosities. They were visible indicators of aerosol concentration at high altitude. The planet's atmosphere had become an optical filter, reshaping how sunlight interacted with air, cloud, and surface. Krakatoa did not permanently alter Earth's climate, but it demonstrated that the climate system is sensitive to sudden injections of material into the upper atmosphere. The eruption became a reference point, a natural experiment revealing the link between volcanism, radiation, and global temperature. In the months following the eruption, the altered atmosphere produced displays unlike any previously documented at such scale. Across Europe, North America, and parts of Asia, sunsets deepened into extraordinary bands of red, orange, and violet. The colors lingered longer than expected, often illuminating the horizon well after the sun had disappeared. The effect was most pronounced at twilight. As sunlight passed through the aerosol-laden stratosphere, shorter wavelengths scattered more efficiently, allowing warmer tones to dominate the visible spectrum. The result was not a single flash of color, but layered gradients stretching across vast sections of sky. Observers described the phenomenon as luminous and persistent. In some regions, the sky appeared almost metallic in tone, with diffuse halos surrounding the setting sun, and occasional reports of greenish glints or even blue-tinted moons in the weeks after. These optical effects were consistent with high-altitude aerosol presence, though the chemistry behind them was not yet fully understood. Artists documented the transformation with unusual fidelity. Paintings produced in the mid-1880s show intense crimson horizons and atmospheric haze once considered stylistic exaggeration. Modern atmospheric analysis suggests that many of these depictions were faithful to observation, preserving visual data long before photography could reliably capture such gradients. Mariners crossing the Atlantic and Pacific reported similar scenes at sea. Without urban light interference, the glow often appeared even more pronounced over open water. The horizon seemed extended, as though the atmosphere itself had thickened and diffused the boundary between sea and sky. The phenomenon was not confined to the northern hemisphere. Reports from Australia, South Africa, and parts of South America described comparable twilight conditions. The aerosol veil had achieved near-global distribution, confirming that the stratosphere connects distant regions through shared circulation. For the general public, the altered sunsets inspired fascination rather than concern. Few associated the colors with climatic consequence. The connection between volcanic aerosols and temperature variation was still emerging. What people saw was beauty, what scientists saw was atmospheric modification. Over time, the intensity of the displays gradually diminished as aerosols settled and dispersed. Yet for about 2 to 3 years, most vividly in the first 1 to 2, the planet bore visual evidence of the eruption. The sky had become a canvas reflecting geological force translated into optical effect. The sunsets of 1883 and 1884 were therefore not isolated curiosities. They were manifestations of a measurable shift in atmospheric composition. The Earth's climate system had absorbed the shock of Krakatoa and responded in a way visible to millions. In retrospect, those prolonged crimson evenings served as a reminder that climate is not an abstract concept. It is a physical system capable of responding to sudden geological impulses, transforming light, temperature, and perception across continents. In the years immediately following the eruption, meteorological records began to reveal measurable deviations. Surface temperatures across parts of the northern hemisphere, and globally, declined by approximately 0.5 to 0.6 degrees Celsius in the year after 1883, with lingering effects detectable for up to 5 years in some datasets. The change was not dramatic enough to trigger widespread alarm, yet it was statistically significant when compared with preceding years. The cooling effect corresponded with the peak concentration of sulfate aerosols in the stratosphere. By reflecting a portion of incoming solar radiation back into space, these particles reduced the net energy reaching Earth's surface. Even a slight alteration in radiative balance can influence seasonal averages when applied at global scale. Instrumental records from Europe and North America show a noticeable dip in average temperatures during 1884. Agricultural reports from certain regions described shorter growing seasons and delayed harvests. While climate variability has multiple drivers, the temporal alignment strengthened the causal link to the eruption. Sea surface temperatures also exhibited minor fluctuations, particularly in regions sensitive to atmospheric changes. The interaction between ocean and atmosphere amplified certain regional effects, illustrating the interconnected nature of climate systems even in the absence of modern computational modeling. Importantly, the cooling was temporary. As aerosols gradually settled out of the stratosphere, radiative balance began to normalize. Within a few years, with full recovery by around 1888 in many records, global temperature averages returned closer to pre-eruption baselines. The planet demonstrated resilience, but not immunity. Krakatoa did not initiate a long-term ice age, nor did it permanently destabilize global weather patterns. Its influence was measurable yet finite. This distinction proved crucial for emerging climate science. Volcanic forcing could be powerful, but it operated within definable temporal limits. The eruption provided one of the first large-scale case studies linking atmospheric chemistry to global temperature variation. It allowed scientists to observe how sudden injections of material into the upper atmosphere could alter energy distribution across hemispheres. Decades later, as climate research matured, Krakatoa remained a reference event. It demonstrated that the atmosphere is sensitive to rapid perturbations and that global systems respond predictably to changes in radiative forcing. The lessons would inform future analysis of both natural and anthropogenic influences. The disturbed climate of the mid-1880s was therefore not an isolated anomaly. It was an early demonstration of planetary feedback mechanisms. A volcanic island in the Sunda Strait had provided empirical evidence that the Earth functions as a connected climatic system. The eruption of 1883 did not simply reshape an island or redden the sky. It offered a measurable glimpse into how geology, atmosphere, and temperature are linked in a single, responsive framework. The eruption of Krakatoa occurred at a moment when scientific instruments were becoming increasingly precise and globally distributed. Telegraph networks connected observatories across continents, and standardized barometric measurements allowed atmospheric disturbances to be compared in near real time. For the first time, a volcanic event could be tracked beyond its immediate region. The pressure waves that circled the globe provided compelling evidence that Earth's atmosphere behaves as an integrated system. Data collected in India, Europe, and North America confirmed that a single explosive event had propagated measurable effects across hemispheres. The planet's atmospheric envelope was no longer an abstract concept, it was demonstrably connected. Equally transformative was the documentation of stratospheric aerosols and their climatic consequences. Scientists began to understand that volcanic eruptions could inject material high enough to alter solar radiation at global scale. This insight would later inform the study of radiative forcing, a central concept in modern climate science. Krakatoa became a reference point in subsequent research on atmospheric chemistry. The relationship between sulfur emissions and temperature variation observed after 1883, established a framework for analyzing how particulate matter influences energy balance. The eruption functioned as a natural experiment long before controlled experimentation was possible. In the decades that followed, climate researchers repeatedly returned to the data from the 1880s. Temperature anomalies, optical observations, and barometric records provided a rare alignment of geological event and atmospheric measurement. The evidence strengthened the emerging understanding that climate is shaped by both gradual processes and sudden impulses. The eruption also underscored the value of international scientific collaboration. Observatories separated by oceans contributed fragments of a larger pattern. Only when combined did those fragments reveal the full scope of the disturbance. Krakatoa demonstrated that planetary phenomena require planetary observation. As the 20th century progressed, additional eruptions would confirm and refine these findings. Yet Krakatoa remained distinctive in scale and documentation. Its effects were visible to the public, measurable by scientists, and traceable across multiple domains: geology, meteorology, and oceanography. The unusual sunsets faded. Temperatures stabilized. Trade routes resumed. A new volcanic cone would eventually emerge in the same strait, rising from the caldera left behind. But the intellectual legacy of 1883 persisted within scientific literature and climatic theory. The volcano that changed the planet's climate did not do so permanently. Instead, it revealed that climate can change in response to sudden natural forces. It demonstrated that the atmosphere is dynamic, sensitive, and interconnected with the deeper processes of the Earth. Krakatoa's eruption remains a reminder that the planet operates as a unified system. A fracture in one narrow strait between continents was sufficient to alter light, temperature, and atmospheric pressure around the globe. In understanding that connection, modern climate science began to take shape.